The gravity of the time is such that every new avenue of peace, no matter how dimly discernible, should be explored. Never before in history has so much hope for so many people been gathered together in a single organization. You will provide a great share of the wisdom, of the courage, and the faith which can bring to this world lasting peace for all nations and happiness and well-being for all men.
This is the show Titans of Nuclear, and today we have a great guest with us, Cesare Frepoli, who is the president and CEO of the FPoli Solutions, as well as a PhD of the Penn State University. So the company of yours, the FPoli Solutions, specializes in the management and the execution of projects for industries like nuclear, but not only, it's also aerospace, for example, and other industries. Welcome to the show.
Thank you. I'm glad to be here.
That's amazing. So yeah, right now you're the CEO, you're the principal consultant of your company. But what we like to start with is actually the background. Where do you come from?
Sure.
How is it possible that a person like you made such a long, very successful career? We want to know everything. So let's start from the fact that you're a master of Milano, of the famous Politecnica di Milano.
That's right.
If I'm not wrong, it was in 1990, right? And so
yes,
yeah, I'm really interested
in
the atmosphere. Like, how was Italy at that time regarding nuclear?
Right. No, actually, those were a very interesting time. As a matter of fact, I started my master program in Italy in nuclear engineering. I was always passionate about nuclear engineering since I was a young kid, so there was no matter of where to go, what to go. And early 80s, the 80s were very good at Italy because Italy was following actually the French model. They had what's called at that time piano unificato nucleare, which means that they were planning to build many nuclear power plants and basically get to where France is actually today, with 60-70% of the electricity energy coming from the nuclear, and that was the intent. So I started my schooling in the 85, 84, and I was really determined to go with nuclear engineering. And then what happened? 1986, we had the Chernobyl accident, as you know, in Europe, and of course there was a lot of was probably heavily politicized, and many things happened in Europe around that time as a consequence of the accident, and the sentiment toward nuclear kind of deteriorated. And also Italy, they decided to have a popular referendum in 87, and as a result of the popular referendum, the whole program was canceled. So what happened is I even had a professor at the Politecnico di Milano that say, well, if you guys want to continue in this path, but maybe you should reconsider. Instead, I was determined, I'm going to stay here. I really believed in that technology as far as the energy solution for the future. So I stick on it. And then I graduated in the 90s. So then the question is, where are you going to go work, right? Because Italy there was not much going on. There were maybe some basic research and things like that. So I started exploring opportunity. I started actually in France. France was probably the most promising country to go, especially close, just across the border from Italy. That didn't, it was kind of difficult to get there. Then went to actually the US consulate and say, well, the other country was, United States, obviously there was lots of activity going on in the nuclear at that time, and how I can get there. This was kind of around the 90s. There was lots of discussion of passive, more safe plants like a P600, a P1000 in those days. And they suggest actually, well, if you find a job in a company in Italy that work and collaborate with company in the United States like Westinghouse, General Electric, or even Framatome at the time, that could be maybe a way to go. And that's what I did. I kind of turned turned down all other offers, and I ended up to be my first employment at Ansaldo Nucleare, which is kind of the nuclear vendor in Italy. And then I kind of worked my way through in the first year or so to get an assignment in the United States. Ended up to be sent to the United States as a guest engineer at Westinghouse in Pittsburgh, where I am today, actually, back in around 92, 93. So I was there for 6 months. It turned out to be that I ended up to stay there for 3 years, up to the 96 time frame. And then at the end of my assignment, obviously I was very happy about my experience there, and I went back to Italy. And I thought I was kind of done with my US experience at the time, but I was still kind of missing going back, kind of the environment, that was here as far as the nuclear energy. Also, there was lots of development going on in those times. And what happened is that was sometimes some luck or what it is, but my former advisor of Westinghouse, they became professor at Penn State University. One night he called me and he said, "Hey, I'm setting up a thermohydraulic group," which was my background and my experience here at Penn State University. "If you want, you can come here and be my research assistant, and then you can pursue your PhD studies." And obviously I had a job. I have a young family at the time, but I was so determined. I didn't spend much time to think about it. I think it was just within a week, I call him back and I say, "I'm coming." So I kind of quit my job from Italy, and I kind of jumped in the adventure. We flew in the United States, and this was 97, January 97. And then that's where I started my PhD, do some research with the Nuclear Regulatory Commissions. It was funded by the Nuclear Regulatory Commission in my thesis, and ended up to graduate in 2000. And then again, it was kind of a big circle going around. And then as I was looking for my first job at the PhD, I ended up to work at Westinghouse again. And now I was as an employee. And so that's kind of how I got here. It was kind of a long story, but that was kind of, I thought was always interesting to share, and that kind of was kind of a little bit of a dream for me to start working in the nuclear, really in a place where that was kind of rewarded and there was progress going on.
I'm actually interested first with something that's not non-technical. What came to my mind when listening to you was that there is a little bit of stereotype among young people, like students, late students, that either you finish your university and you go straight to PhD, or you go to industry and you stay there forever. What are your feelings about this? Was it an asset of yours, an advantage, that you had already some experience in the industry and then started the PhD?
Oh, it's a very good question. And actually that was something when I was facing that decision, was something that I was a little bit of a dilemma, is the fact that by the time I decided to do my PhD, I was already in my early 30s. So I had basically 7-year working experience between completing my master in Italy and then starting my PhD. So I was kind of an old student, if you want to call. But it turned out that to be an asset. And the reason is that working in the industry for those years, it gives you like a structure in executions and planning. And so I was actually typical PhD in the United States could be in excess of 4 years and maybe 5 years. But because of that, I was able really to work with the professor, had a good program, execute the program, and basically graduate in 3.5 years with the PhD completed. So I think at the end was an asset. Was also interesting to go back in a school, in a different school environment. I graduated from Italy, going to the United States, much more research, and it was actually a refresher somehow to go back to classes. Learn more advanced classes. So no, I think it was a positive. It was not actually a problem. There was that gap. It was a good thing.
Great. Okay, thank you for this answer. So one of the things that I really caught in your bio was, in your early bio especially, your contribution to the integral test facilities. And so I would like to ask you first to maybe explain to everybody what is an integral test facility, how does it work, and what is its utility for the research, but also for the industry?
Right, right. So one thing that has always been in the background of my career has been pursuing safety analysis. So safety analysis is it's kind of a very, how to say, complex work around the licensing and the design and basically proving the safety case of a nuclear power plant. So obviously you cannot have an accident on a power plant. You want to avoid that, right? So, but you want to have the system design that it can mitigate, even if you have an accident, what the consequences of the accidents are, just for the public safety. So the integral effect tests are really a very important and key component, because those are really the kind of the proof and the only data that you have that you basically, what they do with these integral effect tests is a subscale simulator of the reactor, where obviously they don't have a nuclear reaction to provide the energy, but they simulate the nuclear reaction with like electrical heaters. And then it's a subscale. So similar, maybe a parallel in the aerospace industry, where they may have like wind tunnel test of Boeing 747, right? To make sure that the fly in all kind of conditions are safe. So that's kind of a similar in the nuclear industry. They build this test facility, which are subscales, could be different type of scale. Typically you do also multiple scale, because the scaling is also an important issue. And you simulate accident and you simulate events. You see how the system perform, how the emergency system comes in, and how you're able to maintain the core cool and what the consequences are. And then you use all that data. And this is data that's been accumulated since back to the 1960 up to today. They're still generating new test data with the new reactors. And then what you do, you use computer codes to benchmark against that data. So that's a way we'll call qualify the analytical tool, so that you know that the simulator, they are actually predicting reality, and where the reality is, in this case, the test data, because obviously there is no accident on the field. You try to avoid this, right? So that's a way to replicate conditions, adverse conditions, on in a safe way, using those facilities.
That's really interesting. And so, what are the challenges of construction of such a facility? You said already that the scaling, different scales also. Please tell us more about that.
That's right. So you tend to, obviously there are this kind of a technology that evolved over time. There are some criteria or similarity criteria that you try to, it's a mathematical apparatus where you say, like, for example, you want to preserve the pressure, but maybe you cannot, because of the cost, you cannot really preserve the scale in terms of flow area. So you do what is sometimes called a pressure over volume scaling rationales. But there are many more sophisticated, but really it's a mathematical algorithm that proves that what you are testing in the apparatus has a similarity with what would happen in the full-scale plant. And as again, the parallel in the aerospace industry, when they will use subscale model, or even in the for marine constructions, from a shipyard and things like that, there are criteria to say, could be like maybe the time is accelerating the test facility, or the time scale is different to preserve certain quantities, right? So it's a whole discipline, actually, the scaling, which is something actually we still do in my company. And like, for instance, even new scale, we do some work associated with the scaling, working with those areas, which is also an expert in the scaling techniques. And yeah, it's a very important part of the scaling and applicability of the building the safety case of a power plant.
So each kind of scale will preserve one or several parameters, but we all know that the accidents are very parametrical.
That's right. That's
events.
right.
So how do we go from the test facility to actually understanding what happens inside of the core or inside of the nuclear installation in general?
Right. So you typically combine several integral effect tests at different scale. Could be like a scale of like a semi-scale is one of the older test facility as a scale of 1/700. So it's a very, very kind of spaghetti representation of a nuclear power plant.
It's a very good Italian parallel, right?
Italian part, right? That's right. And then because really that's how it looks. You know, you have this pipe that I like really spaghetti shape. And then you have larger scale. Larger scale in the nuclear industry, it could be like 1/50. Like Loft, for example, it's another one that in my area, it's well-known test facility from Idaho National Laboratory. It could be, there are actually full-scale prototype, like there were a program developed in the 80s. This is called the UPTF, Upper Plenum Test Facility. It was a consortium between Germany, United States, and Japan. It was a very expensive test facility. The test was conducted both in Germany and Japan, and then US was responsible for the instrumentation and control. And that was a full scale. And why they had to go to full scale is because there were phenomena that could not be represented in subscale, like multidimensional phenomena. And so they created this very large test facility that was like representing what at the time was a large PWR design, German design. And then you use different point in scale to see also understand how the phenomena evolved with the scale, what the similarity are, so that then you have different points and you can extrapolate. When you do a simulation at subscale, you now have basis to extrapolate to the full scale behavior, right? So you can predict the full scale behavior because you have tool that has been validated at multiple scale. And so now the tool can learn what the behavior is at different scales, so it can predict with fidelity the behavior at full scale.
It's very interesting. Another topic that I could really catch in your bio is the licensing and certification, which is, I guess, partly related to the integral test facilities and the knowledge that we get from them. Maybe first let's start from also defining what is the licensing, what is the certifications, what are its objectives?
This also actually even recent has been a continuous evolution also from the Nuclear Regulatory Commission and the industry as a whole. So traditionally in the past, like in the 80s, they have like a two-stage approach where they have like a preliminary safety report. So it was like the applicant could be the designer of the reactor, Westinghouse, or the utility applying, or what have you, basically constructing all those body of evidence, kind of constructing the safety case for the power plants. That was submitted to the Nuclear Regulatory Commissions, and then they were doing the review process, and you get a final safety kind of approval of the design. You know, that was the final safety analysis report, or UFSR. And then after that, though, there were multiple stages where now you're approved for the design, but then you have to apply for the site permit, and then you have to apply for the construction. So it was a multi-stage process. Back in the early 80s, 90s, they kind of update, there was a modernization, a first wave of modernization by the Nuclear Regulatory Commission to kind of streamline this process. You can imagine it's very costly, very expensive, takes a lot of resources. And so the idea was how we can simplify this process for new plants coming. And I'm talking about around the 90s, where like design like the P600 or AP1000 from Westinghouse are passive with passive safety features. So they developed what was the 10 CFR Part 52. And that was what introduced the concept of design certification. So you basically, the process was you kind of similar as before, but you get to certify a design, and then you only have certain specific item that you have to address when you actually go and build it and construct no specific site. So there are maybe site specific, but really as a whole, the design is certified. Essentially, you have your safety case that is the Nuclear Regulatory Commission, kind of bless and say, yes, this is safe for the public, and can be constructed. More recently, as you know, there are lots of startups and lots of movements, particularly in the United States, for advanced reactors, which are now exploring a wide range of technology, probably of the order of 10 startups. These are like the Kairos Power, the X Energy, TerraPower, funded by Bill Gates, and many others, right? And those are actually introducing a variety of technology that are not covered in the methods of regulating that they had before. And so actually quite recently, starting from 2018, there has been a what they call a licensing modernization plan. And so they're naturally moving in this Part 53. And what the layer they're introducing on top compared to the old way of regulating is what they call a risk informed. So it's where you fold like probabilistic risk assessment or those type of analysis into the design cycle. And that's actually what we do in my company. We develop tools and technology to kind of help the applicant to do those complicated licensing process, but hopefully to also reduce dramatically the cost, which remain quite high for the power plants to apply and get the design certification.
Do you think that the fact that we have a new wave of reactors coming that are kind of, I don't want to say revolutionizing, because we already know these technologies, they existed before, but bringing a new dimension to what nuclear is, it doesn't need to be always the same. It doesn't need to be only one technology that is prevailing, but several different technologies who then will be copy pasted into modular installations. Do you think that this fact that they are so different, like starting from kind of scratch with the licensing, may it help in actually developing the regulations to make it more streamlined, not so slow and not so complicated to achieve, and not so costly, most of all?
That's right, and that's, I think it's in my opinion, is still a problem that has to be solved. Obviously, these the only near experience, even before what I was referring before, is the 10 CFR Part 53, which is just the recent rulemaking, which is like an evolution from the design certification process. But the only point in recent history that we have, for example, is NuScale. NuScale got the design certification, I believe it was 2019, and don't quote me there, but around those years. So it's probably the most recent example. But the other one, are still kind of, some are submitted, and I think the push from the industry standpoint is that there is so much margin in this design that they should be able to kind of defend the safety case in a much more streamlined way. However, you still have to face the regulator and go through all this scrutiny and build all those evidence that kind of make your safety case. So I think the challenge still remains on how you can close that gap in a very efficient, and then you can make these reactor economical, because they need to be economical to license, so that it's a short road to get there to the deployment, but also to maintain them, right, as component age. And also, I think a challenge maybe for the new plants would go to gain enough data on the like new piece of equipment that don't have like the history of light water reactor technology, for example. But they do indeed have a large margin compared to the more traditional. They also tend to be quite simple, especially like micro reactors that can be transportable. The scenario are very, very simple compared to the much complex machine that are operating right now. So I think the promise is there. Now, I think that the next few years we'll probably know more, but I feel the challenge is there. But I think the other thing we're trying to use, especially in my company, is to use digital technology, machine learning, AI, and all these infrastructure, and kind of coming out from the digitalization of the world to help and facilitate and accelerate the design, and also manage the data, track the information, make it easy for regulators to review, because one of the key goals for them is to be transparent, to be scrutable, so that if you build a safety case, you understand why, what the rationale is. It's a very logical pattern and with a very voluminous amount of data. that's to be generated.
Listening to you about before the integral test facilities, it made me think actually that how it is with research that a different country can collaborate and like share the facilities. People from Germany can come to the US and use the installation and take some universal conclusions and take them home. However, with the licensing certification, it's not really so easy. Do you think that like it is any close future of our hard work and of our focus on the licensing development that we'll be able to harmonize the regulations in this respect, be it globally, but at least regionally, let's say only in Europe or only in North America and so on?
Yeah, that's I mean, now many of the test facilities we discussed were, for the most part, were international program. I mentioned before, even the one critical that is used by the entire industry was a collaboration between United States, Germany, and Japan. That was very important. There are many other like OECD and other organizations that try to make that data more public, and I think over the years it become now, like, for a small company like us to be able to have access to a very large amount of data, which a lot of this data now become of public consumptions, and maybe the challenge is more like organize that data. Particularly because you have to deal with data generated today, with the instrumentation of today in 2020. At the same time, you may have to go back to some of these reactors, go back to technology that was explored in the 1960s, or you have experiments that go back in the 1970s, in the 1980s. So there is a whole set of legacy data, and warehousing and processing, organizing that data. It's probably an area where coordinated development or international effort can help, because at the end of the day, otherwise you have every applicant to kind of go through the same amount of work. It's very inefficient, and that's actually one area of this we call it data ontology, to classify this data. We created some tools. You can see this in our website, but that was also how we can make this all information more accessible to the public. And now that there are more startups, and that can drive further innovation, then we need to facilitate that process, that kind of remove barrier and be able to share that incredible amount of knowledge that was created by the nuclear industry in particular, for the safety case of the plants.
But so is it possible to remove these barriers in terms of licensing and design certification anytime soon?
I don't know. I think the NRC, as far as I know, the NRC is still kind of taken as obviously there is the IAEA with the safety guides and things like that. The NRC tend to be sometimes the example for many countries, but there are differences. And yes, it's what you're saying. It's a challenge. If you have to take a new design. And just because it's been approved in the United States, it's maybe a good step ahead, but it's not the job completed. Say if you have deployed the same plant in UK or in other countries, right? So I think that's remained a little bit of a challenge. There's been always a talk about harmonization, but the way regulator approach the licensing it's not homogeneous, I would say. Still kind of there are different facets that you need to face every time from different countries and different nations.
Okay, so it's not that easy as let's work together, we will work it out. Let's
yeah, it's not straightforward. It's not straightforward.
The nuclear regulators, I don't know, of Europe, and let's just find some compromise, please.
That's right. Now there have been attempts, like in the past. Also, there was like a consortium of utility for, especially based on my experience when I was working at P1000, to define like a uniform. There was like a uniform aggregation of utility from Europe to define common ground for the requirements for the design, right? So that when you comply to those requirements, then the design can be applied in Italy, as in France, as in UK, and I think there have been always attempts in that direction, and those are very useful for sure.
Can you tell me a little bit about the EU Commerce project? And
this was an old one. So
that it's very, very interesting. Like, please tell me what were the initial conditions? What were the developments of the project?
Sure. So this one was actually, I was referring before when I was in the United States, a guest engineer, and then I went back in the mid-90s back to Europe, and then I worked on some European program. And one of the projects that I was involved at the time was this EU Commerce project, which I think I've even forgot what the acronym of Commerce stands for, but it was, the test was conducted in Germany, was associated to actually a French plant, the Framatome EPR design, where they wanted to have the ability that even in the case where you have a very severe accident, which is almost the one that you don't want to have, right? But and it's where even the emergency system cannot cool the core, and then at that point the core melt, and then it kind of penetrate through the vessel. The vessel essentially that's containing the reactor core fail, and then you have this molten material. And so they were planning to design at that point was this core catcher, which is essentially kind of a basement inside still of the containment, so that then there was no radiation of the public, but then be able to collect these corium. And that's where COMAS, I think, it probably is a German acronym. That's why I don't remember what they stand for. But the idea was to simulate a prototypical corium, and then how that spread. And the idea was that you spread, think about a lava flow, where you spread over a large surface, and you develop a crust, and then by that you can stabilize the material. And so even in that severe condition, you're still in a safe situation because all the radiation has been contained within the containment. So the test was actually simulating real material like UO2, which is dioxide of uranium, which is used for the typical light water reactor technology, and actually heat it up and melting that together with the zirconium cladding, which is the material they use to put as a cladding to the pellet of the fuel, and then had all that melt, and then open the gate and see how the behavior of the spreading was. So yeah, I was actually I attended some of those experiments. They were kind of impressive. You were behind the glass and see all this these very high temperature materials spreading on the basement, and then using different material like could be concrete, metal, or they were using more exotic substrate to see which one was performing better for spreading the material. And this was what called the core catcher concept design that is actually embedded in one of the French Framatome reactor, like the EPR.
EPR, yeah. So was the result found, or was it just a set of dead ends that was known that they don't work?
No, I think it generated some data that was used internationally to validate some of those design. I believe, obviously, there were some set of tests that were proprietary that I was not involved in. And the portion I was involved was a set of experiments that they decided to open up to the European, that was actually funded by the European Commission. And that's what, a few tests that then international that could be used to benchmark tools again, at scale, and see how that spreading behavior of the melt could be handled and modeled.
So these are the non-proprietary.
There were some non-proprietary set, and then there were probably, I'm assuming, the test facility was also used and dedicated for the designer. Arriva was, as you know, was Framatome and Siemens together, that they had this, they created this joint company, and I think that was they were the most interested in design because they actually implemented that device into their reactor.
Yeah, we are talking a little bit about the concepts that are technical, but not very much related to numbers and to what you're doing on everyday basis, because you are actually an engineer who is very much related to the computational field. And so the integration test integrated facilities that we are talking about, the EUCommerce project, all of these phenomena that you're studying, you are actually calculating based on the experiments that are conducted. So what are your main fields of the computation? Is it the thermohydraulics? Is it rather the heat transfer?
It's kind of a combination of different disciplines. I mean, it's background, and also the background of the team is thermohydraulics, but some of them are also, as a background, they are core engineers, meaning they understand all the thermomechanical aspect of the core, what happened to the core when it was irradiated, during the operation, the degradation of the materials inside and things like that. So, I would say, and then the core physics, like the neutronics and how the power gets generated and so forth. So yeah, it's a multidisciplinary, a multi-physics approach when you do this type of analysis, and you have to look at different type of tools, different type of codes that you have to use to simulate different all these, and obviously different set of experiments to benchmark those tools. But yeah, I think in the team overall, I mean, I kind of started as a thermohydraulics and kind of evolved more like in core engineering, and my team is kind of diverse in that segment, in the whole sector for the safety analysis.
Can you give us a little bit of a feeling of how much one person is able to do right now in the nuclear computation? You said already the multiphysics analysis. Does it mean that one engineer is able to start from the core, finish on I don't know, CFD analysis? Just how compressed is the calculation power right now in terms of what we are able to do as an individual?
Yeah, I think that actually was a motivation why I started the company in 2012, was because what happened in the computational capability in the world. So before, like when you go back like 20 or 30 years ago, yes, this type of computation require a very expensive infrastructure to run those calculations in terms of manpower, but also really servers, hardware that you need and expenses that you need. And then, as you know, there's been a kind of a revolution with the cloud computing, where and it turned out to be an opportunity for like that I identify, when I started the company and say, I don't really need to be in a corporate to be able to do those type of complex analysis. There is a lot of things in the open source community that you can leverage. There are lots of things created by national laboratory which are available to you at basically at no cost. And sometimes it's really the ability to integrate all those parts. And then when it comes down to the infrastructure, when you look at the cloud computing, like Amazon Web Services or Microsoft and all that, you kind of create very easily, kind of scale up your infrastructure to be elastic and kind of grow with the business, right? And so you're not like in the past, maybe you need like a group of 30 people and very expensive computer, $100,000 to be able to do those analysis. And think these days you can probably do, set up the system, apply for subscription with AWS or Azure or what have you, create an instance, create your infrastructure for running those calculations, and then be able to also work remote and stuff, especially these days become kind of important. And also you don't need a lot of, I think the technical depth that you need to have is still there. In a way is also broader because it's not only understanding the physics and the engineering, but also you need to be able to master like the advances in the in the digitalization, like software techniques come out and enterprise solutions, web services, what have you. And so it makes you a little bit broader, more holistic view of the problem, not only the engineering, but also the software, the tools. And I think it's an opportunity, especially for new engineers, why they like and all these startups there that come out these days and kind of make it fun to work, because you don't only focus on one aspect, but you can explore a wide variety of things. And it's much easier to do than in the past, for sure, with the technology we have today.
Can you imagine that finding such an engineer for your company who is able to do everything from the beginning to the end, from IT to understanding the phenomena to having actually soft skills to be able to explain your results and because in the end you want to be also selling your services. It's not an easy recruitment task. How does it work right now with finding young engineers? Are they easy to find? Are they looking for jobs? Is the market expanding? Is it shrinking?
No, actually, you're hitting a very important point. Since I started the company, I would say that the most challenging part, but also the most rewarding, has been the people factor. I started with this seed idea I really want to create this dream team where we can collaborate and really kind of change the industry and create some revolution in a way, how things are done. And we can do it better than in a corporate, much more agile and things like that. But then you face the issue, well, you need to set up the team, right? And it takes a lot of effort to make sure that there is the right chemistry, the right skill sets, but also there is a lot of dynamics in how you make people that own what they do and they are satisfied on a daily basis on what they do and develop that ownership. And I think one advantage I found in a small team, that especially people that join my team coming from corporate, is the ability that you're not only like a number where you kind of very specialized in your sector, but you kind of also exposed, talk to the customer. You may, like 1 year after you are in the job, you may be talking to a CEO of another company. They love that. They love that customer facing and that experience to kind of understand what the needs are, and then challenging also to what I'm doing is really useful in the market. Do I really have a business case? So you're not really only executing a task, but make you more like an entrepreneur, kind of a group of entrepreneurs in a way, and a very collaborative environment. And I think when you reach that goal, it's hard to get there. A lot of personal dynamics happening, but it took probably even for my team, we're 8 years since the company was founded. I think we are in a good spot there, and it's very rewarding when you see this dynamic, this kind of everybody being kind of in the flow of things, of creating, and then kind of enjoying what they're doing. But it takes effort to go there. As far as recruiting, I think when you create the right atmosphere and they feel, when you interview somebody, they actually feel your culture. What's your corporate culture is, what's your mission is, what's your vision is. It's easy to attract people. And I never had a problem to a gap in that sense. When there are needs, always as a small business, you need to calibrate your resources to the business as to grow organically, but it's never been a challenge to find people. It's probably the most difficult is to create that atmosphere of creations that I think we're a good spot now, but it took a lot of effort.
So I guess all the nuclear companies should take this quote home and take the conclusions. I'm wondering, since I'm a person who was facing the challenge not so long ago of finding a job and deciding what my career will be, I can also solidarize somehow with my peers and ask you maybe on their behalf, what a person that wants to become a person like you in the future should do, should think, should focus on. What to do to become Cesare Frepoli one day?
That's a kind of a difficult question. Every story is a little bit kind of individual, right? But I'll say that for me was maybe, I don't know, maybe because I'm coming from another country and I was always curious about traveling and meeting people. I think as I was working through, my opportunity with different companies in my career and then kind of growing there and trying to learn as much as I could within those organizations, were also the ability to, trying to find any opportunity to network, to exchange and to know people. And I think at the end, when I was like in that big decision time in my life where it was like, should I pull the plug and start a company and leave very safe? And I was like a fellow engineer at Westinghouse, so it was a very satisfying job there. I didn't have any particular complaint, but I had that thing. I like to create something on my own. And I could not have done that if it wasn't for really the network of, the reputation in the industry, the network of colleagues, friends, and then be able to, and then that's where all the opportunity came about, was really through that network. And I think creating that credibility in the industry, this external exposure, even when you work like in a corporate, sometimes it's a little bit difficult, but if you try to find opportunity to expose yourself outside and then create that, I think that was probably the recipe for me to be able to then start something on my own, and it kind of was a mitigating any risk, because obviously you can always fail, but that was probably one critical aspect.
Thank you on their behalf. So we talked about attracting people. I would still be interested in actually attracting contracts in terms of the nuclear industry services that you can provide. You said already that you are not only focused on nuclear, but also on other industries. So how are the moods in nuclear industry, in your opinion, and does it help you, or is it an obstacle for the development of your company?
I think it's, maybe the nuclear is definitely an asset as far as kind of forced to be very, how to say, the technical depth and breadth that you have to cover in the nuclear discipline is pretty vast. And so they give you can extend the capability, not only myself, but the leader of the team. I'm always talking about the team and how we can do different things. Like we had opportunity that came out kind of spin off of the nuclear in the renewables, like in the energy storage, like was completely new field for us. But that was because we developed certain technology in the software to manage data, and then as engineer, okay, it was a new problem, it was just a different problem. I need to understand a little bit more, how battery works, how battery degrade, and how they're organized, and they are completely different. Still in the energy sector, not completely different, but you can still cross-pollinate and explore that industry. In the aerospace is also a similar thing. There's also a thing about safety in the aerospace industry and materials of fluid dynamics that we apply in the nuclear that we can also apply in this other sector. And yeah, I would say that as far as the work opportunity, that's the good part, right? Your credibility and being able, they know that you can solve complex problems. Maybe sometimes because there is a lot of overhead in the nuclear industry when it comes to safety and the rigor that we do things, we tend to be maybe on the expensive side when it comes to cost and things like that. So that's a little bit of a challenge we have to balance, because you have to develop certain skill, you have to attract certain engineers, and they demand certain cost. And then you kind of have to make a decision. You want to stay in that complex realm of things and stay with high caliber, which that's what we decided to stay. But it may kind of make you not competitive when it comes to more simple jobs in a way. Okay. Which could be in other industry where maybe the same level of rigor, the same level of knowledge is not required.
So many different industries to explore. What makes you stay in the nuclear field, actually, and and
As I say, it was since I was a kid, maybe because I was reading the books of Isaac Asimov in my time, and there was all this nuclear energy there, and I wanted to do a nuclear engineer. So, and I truly believe that the nuclear solution is still what can save all the environment problem today, because we can do as much as we can with renewable, and that's a very good thing, the evolution of the renewables like wind and solar. But when it comes down to, reliability and really energy at scale, and to maintain the whole system cost effective, I don't think we can achieve the goals that we're expecting to, as far as making the economy carbon neutral without nuclear. Nuclear has to be there, and you can see if there are people like even Bill Gates investing in TerraPower or things like that, because people recognize that. And then all the startups that there are in the United States right now on the advanced reactor, and many are actually privately funded, so they're not really supported by government. So, I mean, there must be a reason, and I truly believe that nuclear is the solution, obviously integrated with all the other sector. Now we also talk about hybrid energy system, where you look at hydrogen generation, and then you consider hydrogen. The way hydrogen is generated right now, you cannot construct a hydrogen economy because they use basically steam reforming of methane. For every ton of hydrogen, you have to put 4 tons of CO2 in the atmosphere, and you use nuclear, no emission. You can use electrolysis and use the nuclear energy to create what they call the blue hydrogen. I know why they call it blue, but it's what's supposed, not there is no emission there. So nuclear is going to be an important part in the energy and for mankind. So that I think is going to stay, and that's why I want to keep working on it and make things easier, and trying to identify where the barriers are, like the licensing in challenging, the licensing, the safety case, how we can prove that, make sure the public understand these plants are safe, because they're truly much safer than any other source, and work in that direction. Create the toolkit that we are able to communicate that to the public.
So what would you like to see in the coming years happening in the nuclear field, and what would you like to contribute to?
Well, I guess we're continuing our mission to support the nuclear industry from more from the software side. We primarily work on the safety analysis and basically providing the toolkit to develop a new design, and also be able to maintain the current fleet operating, because that's the other challenge, particularly in the United States. You can see the last few years there are several plants closing, nuclear plants, because they cannot compete in the current energy economy for many reasons. And so anything we can do to keep those plants alive, and then to build the new plants, the new generation of plants, I think is something I like to continue doing. And yeah, I like to see this new plant, like a new scale or these advanced reactor to be eventually operating. But even more important is that the current fleet stay functioning and operating. I mean, many they were able to demonstrate licensing up to 80 years. And it's really a big disappointment when you see this plant closing for no really a technical reason. And I think we need to find a way to keep them in the energy landscape. Otherwise, it would be very hard to meet those environment goals that as a global, society we want to reach.
Yeah, let's wish for the best, and thank you very much for the talk.
Thank you so much. It was a pleasure.
All the best with your success of your company.
Thank you so much.
And initiate at least a new approach to the many difficult problems that must be solved in both private and public conversation if the world is to shake off the inertia imposed by fear and is to make positive progress toward peace.